No, these are not annoying. These are great. All right. So I need to tell you guys dot products. Dot products are not super, super hard. The only thing that you have to get through your head about these is that it's not multiplication.
Okay.
This is not multiplication.
Should have put X just to make it more confusing.
Okay? This is not, I repeat, not multiplication. It looks a hell of a lot like multiplication, but it's not. So here's a vector, oops, A1, A2, A3. And I'm going to tell you how to dot that with a vector B1, B2, B3. Yes?
So if we're just given sets of three or variables or constants like that, how are we supposed to know if that's a vector or a point?
Good question. I don't know. Context. So maybe if the book said this, right? Or if I said this,
Okay.
A dotted with B is this. Cool. This context would clue you, right? This thing is supposed to be an A, and this thing is supposed to be a B, and they have vector hats, so probably I'm doing vectors and not points. This operation, it should be noted, does not work with points. And so that's a really good question. You guys all see that? What other operations don't work with points? Like we just finished two other operations, right? Scalar multiplication and addition. Yeah, neither one of those work with points, right? There's no sense to this point except longer, right? Like, or this point and also that point, like there's no concept for adding. So if you're doing an operation between two things, right, they've got to be vectors to even start this game.
Okay.
That's cool. All right. So these guys, anybody know how to do this?
I used to. I don't remember anymore.
Okay, I'll just tell you. So you take the first components and multiply them together. So A1 times B1. Am I allowed to multiply A1 and B1? What category of object are those? They're both,
First dimension.
yeah, they're both the first dimension coordinate, right? But they're specifically a coordinate and thus a, no,
Vector.
no, easier.
Point.
Not a point, close.
A number.
They are numbers.
Okay.
Thank you, right? They're just some friggin' number. Can I multiply numbers together?
Yeah.
Yes, cool, good. This operation is allowed. You should check these things in your head.
Okay.
Do I know how to add numbers to other numbers?
Yes.
Oops. So here I'm going to put an A2, B2, right? If this thing had been a vector, would I know how to execute that? Do you know how to add numbers and vectors together?
No. You can't have numbers.
They don't even live in the same place, right? So that operation would be strange.
Yep.
So here I've got A1, B1 plus A2, B2. And then what do you suppose the third thing's going to be?
A3, B3.
Probably A3, B3. Cool.
So we get a single number out of two vectors.
Nice. Yes. Next thing. This whole object here is a number. You guys all see that?
So with the addition, you're kind of, or with the scalar multiplication, you're stretching a vector. When you're doing this, what are you doing with two vectors?
Good question. So this is a nice thing to keep track of, right? Scalar multiplication takes two vectors, right, and turns them into, or sorry, scalar multiplication takes a scalar and a vector and turns it into a new vector, right? Some kind of vector. Addition, right, takes two vectors and turns them into
Another vector.
some other vector, right? This thing takes two vectors and turns them into a number. That seems like there's a lot of information lost there, right?
Yeah.
Because these took 3 numbers in R3 to write down, and so I went from having 6 number pieces of information to only 1.
Moved from 3 dimensions to 1 dimension.
Worse yet, I went from 6 dimensions down to 1,
Yeah.
right? Because there were
Oh.
2 inputs, right?
Oh, okay.
Right, I had 6 numbers here and got out 1 number here.
But it
You
doesn't.
guys all see that? So this is like coarsening, right? Like this is kind of blurry, right? You're not going to be able to tell a lot from this thing. So what can we tell from this thing? Let's try an example.
Is it,
where the vectors go?
does it help us with magnitude?
Yes, it does.
Okay.
So this is going to help us a little bit with magnitude and also a little bit with direction. So let me just try this with a couple vectors just to play around and see what it does. Let's see. So let me do 1, 1, 1 dotted with 1, 1, 1.
3?
Need 3.
Yeah.
3? Okay. I don't know what that means.
What about the zero vector?
Yes!
Nothing.
Okay, let's dot the 0 vector with something.
0.
Okay. Does that... Did it matter that this was 1, 1, 1?
No.
Could be
X, Y,
any.
Z.
Infinity, infinity, infinity.
Don't do that one.
X, Y, Z.
Okay, that seems weird, right? How about, what if I did I dotted with J? You guys remember what I and J were?
Oh, you end up getting 2?
0.
Oh, no, 0. You get 0.
So this is, right, 1, 0, 0, oops, 0. And this is 0, 1, 0.
So you
Yes,
get 0.
get
So you get 0 times 1 plus 1 times 0 plus 0 times 0.
So you end up getting 0.
I get 0.
So it's how many vectors are parallel to each other?
What do you
Something.
do if you try, only did 2 vectors that were the same vector, right? So those are definitely parallel. You guys all with me on that?
What was it?
And we got
3.
3.
Are you adding a magnitude when you're doing this?
There's something about magnitudes in there. There is. It's somewhere in there. It's not totally obvious. What's up?
I have the picture for it, where you cast it down on the other.
Oh yeah, I just don't want to talk about it yet.
You're multiplying the magnitudes when you're doing this.
Oh, there's some kind of multiplication of magnitudes, right? Maybe. This one at least is how long? How long is 1, 1, 1? Square root of 3?
Oh.
So square root of 3 times square root of 3 is in fact 3, right? And this is magnitude 0. And that's, I don't know, but I got 0 out. That seems like maybe I'm multiplying.
Yeah.
Oh, except for this one. How long are these two?
1.
1?
1.
1 times 1 is,
But then they're
Should be
perpendicular
one.
to each other.
oh, but they're perpendicular, so maybe it's,
Doesn't make any sense.
The magnitude of parallel dimensions or something of that nature?
yeah, you guys are actually getting super close. So A times B is the magnitude of A times the magnitude of B times the cosine of theta, where theta is the angle between A and B.
Oh, so when it's 90 degrees, theta, cosine theta is equal to 0.
You guys cool? Yeah, and actually you can dig this out of the law of cosines. So if you draw this picture and dork around with it a little bit, you can find the law of cosines in there. Cool? Yeah.
Never heard of it.
Yes, you've heard of it.
Or at least it was not called the law of cosine.
It was definitely called the law of cosines. So the law of cosines is what? Anybody remember?
C squared equals a squared plus b squared minus 2ab cosine c. It's the Pythagorean theorem with the correction factor, guys.
Yeah, it's the Pythagorean theorem, right? Except you subtract off some amount that changes based on the cosine. Right? This is like, this thing here, you could really think of this as the amount this thing is off of a right triangle. You guys cool with that? If you go look at the other set of videos, there's that digging out of the law of cosines from here, but I'm a day behind this time, so I'm not doing it. Cool? You guys all trust me that it could be done?
Yep.
Okay, so you can dig this. Let's check that we were working, that all of these were working. What's the angle between these two?
Oh.
0, right?
Yeah.
So that cosine is 1, and I should multiply the magnitude.
Yep.
Cool. What if they point in opposite directions? What do you get?
-1, right?
Like if you did 1, 1, 1 times -1, -1, -1.
Cosine of 180, which gives you -1.
Yeah, so you would get the magnitudes multiplied together with a flip on the sign, right? So you get -3. You guys all see that?
Yep.
So you can do something kind of cool with this. You can tell whether the angle between two vectors is acute or obtuse.
Oh, by whether it's positive or negative.
Yeah, if it's positive, right, they're kind of close-ish to parallel. And if it's negative, that means they point more in opposite directions.
So how does this work with the zero vector since it's like every direction or no direction?
Good, perfect. How does it work with the zero vector?
There's no.
You get nothing out, right?
Yeah.
You guys see that? Because there's no magnitude. You guys see that?
Okay. Oh, it's just because there's no magnitude. It doesn't matter what the cosine of theta is.
Yeah, exactly.
Okay.
You guys see that? So, what is the use of this thing? Like, I can tell this funny thing about acute or obtuse, but to be frank, that's not that useful.
It was like there was like homework problems that were unique angle, like relative to.
Yeah, so you can find the angles between two vectors using this thing, right? Because you can calculate how long they are.
Yeah.
You can calculate the dot product, and then you can take the arc cosine of some kind of appropriate quantity. So that's kind of convenient sometimes. Like if you want to find out hip and valley joints for making a funny shape out of plywood. You guys know what hip and valley joints are? No?
Okay. Valley.
I need an object that's funny shaped. I don't have one.
How about?
Oh, this sucks. I didn't do a good job. I'm sorry. Here's a funny shaped object.
Pyramid?
Yeah, suppose you wanted to build this out of plywood, right? You want to build a little tetrahedra out of plywood. What do you set the table saw at when you run these pieces through? I don't know. You need to use this thing to figure that out. So, my wife is going to build a climbing gym in downtown Sonora. And so I'm going to get a lot of practice with this, and so are you all, because God knows I'm not going to do all the calculations by myself. So we'll talk about this some more later on the test. No, there will be some kind of project for each of you. Like, here are some planes. Calculate the angles that I need to set the table saw at. The most useful thing for this is just if A dotted with B is 0, then you could do even better than that, right? So if you get 0 out of the dot product, yeah, then they should be perpendicular, right? Okay, really.
What about the zero vector?
What about the 0 vector? So what do you need to note here?
or A. Well,
Need to note that because we said this, right, 0 is perpendicular to everything.
And it's parallel to everything.
Yeah, but it was also parallel to everything. The 0 vector's weird. Get over it. It's fine. Okay?
It's all knowing.
But I don't know about that. At the very least, right, this is just to make things easy. Otherwise, I'd have to exclude the 0 vector from this. But in this case and in the other case, I can just get away with saying the 0 vector is parallel to everything. Fine. The 0 vector is also perpendicular to everything. Fine. Whatever. Cool? You guys all good with that? Why is this true? Can we prove this? Where does this come from? So if A dotted with B is 0, right? So if A dotted with B is 0, that means, right, that the magnitude of A dotted with the magnitude of B times the cosine of the angle in between them is 0, right? Okay, so if one of these is the 0 vector, that would make this true, right? Okay, I've already dealt with that by just saying the 0 vector is perpendicular to everything. You guys all good with that? So let me just assume A and B aren't the 0 vector. In that case, I can what?
Assuming that theta is 90.
Yeah, I could divide by these magnitudes, right? So if A isn't the 0 vector and B isn't the 0 vector, then the cosine of theta is 0. And cosine of theta is 0 when theta is 90 or odd multiples of 90, right? Specifically, the two I'm going to be interested in here are what? So theta is pi over 2, or theta is, I don't know, it depends on how you measure. I'm going to throw negative pi over 2 in here because that pleases my sense of aesthetics. Right? So that's a picture like this, right? Here's a vector A. Here's a vector B. What would you say the angle between these two is?
Negative pi over 2.
Yeah, you might just say like negative pi over 2 as the angle. That's a little bizarre, right? Because really this is 90 degrees anyway. The angle between these things should be 0 to 180. But you shouldn't need to say negative pi over 2. Whatevs. Either way, I'm going to assume that means perpendicular. You guys cool with that? Okay. Check, check.
Doesn't matter how many times it rotates.
No. Because you wouldn't keep track of that information, right? If you're calculating the angle between two vectors, you would never go all the way around. You would just go to it. And you would do that in a close, positive way. That's why you could kind of delimit this between 0 and 180, right? Is all good? Is that going to change if you go to higher dimensions? Yeah, you should think about that. It won't, because it turns out that two vectors are always going to make a plane, and then you may as well be in 2 dimensions anyway. You guys see that? That's a little subtle, right? Okay, cool. Questions on this?
we're flying.
Yeah, then it won't make a plane. That's true. Thank you for pointing that out and making me feel dumb.
That's why we state that A cannot.
So it either makes a plane, right? Or it makes a one-dimensional space, whatever. Cool?